Welcome to Evolving Ideas. I'm Elaine Smitha. We have in studio with me today Lieutenant Colonel Thomas E. Bearden, who is a retired military, I need to say that. And he is president of the American Association of Distinguished Scientists and nuclear engineer. He's also president and CEO of CTEC, Inc. Welcome, Doctor. This is not Doctor. It's not Doctor. It's Lieutenant Colonel Bearden. Thank you so much for coming.
Thank you, Elaine. It's a pleasure to be here.
Well, free energy is what we're going to be talking about. You come with a vast knowledge in that realm, and I'm eager to bring your knowledge to my viewers. So we need to start off with, what is free energy?
Well, it's really simple. We're talking about, let me give you a comparison. It's easier with a comparison. Suppose you wanted to power a mill and you had a nice river with a nice fall in it sitting out there beside the mill. It would be nice if you would take a gate and make it where it would swing out into the river and divert some of the water on the high part, bring that down in the ditch across the wheel, a water wheel attached to the mill. And the river wouldn't miss a little bit of water, and it would furnish you some power to power your mill, and your mill would run, and it would grind the corn and grind the other stuff that mills do. And meanwhile, you'd be taking the power directly from nature. You wouldn't be burning any hydrocarbon fuels, you wouldn't be polluting the biosphere or any of those things. It turns out that in electromagnetics, there are such rivers of energy, many, many rivers of energy. Very few of which we're trying to actually tap in the fashion we would tap the river to power the mill. So the free energy, the term free energy, loosely means we're trying to go after the energy flow that's already in nature or that we can make occur in nature very easily. And then we wish to extract a little bit of this energy flow and power our devices, our circuits, our motors, our heaters to heat our homes, and hopefully the motors to run our cars and get rid of the pollution of the planet. Right. So basically we're trying to tap energy flows that are already there.
And so this is also known not only as free energy, but alternative energy or alternate energies, and but it's not really free, is it?
It's not free in that you have to make the water wheel when you make the mill, and you have to dig the ditch.
Right.
So it's going to cost you a little bit, but then we use the term over unity.
Yes,
you put
that was
in
the term
a little bit, and you get out lots. So what we're really talking about is that for a very small expenditure of work that we have to do, energy we have to furnish to do some work, what we hope to do is get back much more energy to do much more work for us, very cleanly. And so that we call over unity. We put in a little bit, we get a lot back.
Now, this is not a new concept. This has been going on for a long time, hasn't it?
Oh, of course. Everybody that ever put a sail on a sailboat is using a free energy system. He's tapping the energy in the wind. Everyone that we've had water mills for centuries. We've had windmills. Look at Holland, for example, the windmill today.
That's right, that's right.
We're playing with other alternative forms where we're trying to tap the wind and the ocean, and those have not proven too successful. The most successful today we've had of the conventional alternative over unity systems would be your hydroelectric power, where you actually dam rivers and tap the energy flowing in the stream.
Now, Nikola Tesla was involved with this, wasn't he?
Yes, Tesla once, in his later life, he built a free energy device which he used to power an automobile, one of the old Pierce Arrow cars. His nephew who rode in the car with him on a test drive is still alive, so he remembers the drive very well.
Wow.
But he did actually power an automobile with energy taken directly from empty space, from the vacuum. By the way, today, I'm happy to report that in the last 2 years, the U.S. Patent Office has officially recognized the vacuum as a source of energy. It's been known for 50 years in physics, but only in the last 2 years has the U.S. Patent Office recognized it officially as a source of energy, and they have actually issued some patents now for extracting energy from the vacuum.
Really? Okay, I think that would lead us to the next step is, What's a vacuum? How is it used? And the misunderstandings about force and force-free energy.
Well, conventionally, we're taught that the empty space is just inert.
Like this.
It's just an emptiness sitting there with nothing going on. Well, we know today, and we've known for many, many years, 5 decades, we've really known experimentally as well, that that's not true. In fact, it's filled with enormous energy, but the energy is not organized. It's going every which way. But it is enormous energy. And in fact, it is so much energy, there is so much energy in space, empty space, the vacuum, that it's mind-boggling. For example, Wheeler made a calculation showing that 1 cubic centimeter, which is about the size of the tip of your little finger, has enough energy in it that if you were to condense it into mass, you would have more mass than is in the observable universe seen by the largest telescope. So there's no shortage of energy.
No.
The problem is in getting the energy out and collecting it and using it.
I know when I did an interview with John Hutchison a few years ago, he said we have enough energy right in this much space, he said, to run the universe, That's all, it's all compressed. True. It's right here. And he's definitely working with energetic forces in what he's doing.
Yes, he is.
And we used a little clip from something that you had said about him on that show. So explain this vacuum, because I've seen you have some charts on that demonstrate that, but can you verbally explain that?
There are 2 ways of looking at energetic processes. One is to look at them with vibrations and waves, and the other is to look at them with particles that are moving. One we would call a flux, a lot of particles moving in different directions, and another we would call waves, we would call vibrations. Excuse me. So if we look with the particle view, the vacuum then would be a vast series of incredibly dense little particles forming and unforming all the time. I'm going to wash out on you here.
Here, let's have some water.
Anyway, we have what we call virtual particles. It only appears out of nothing, disappears back into nothing very rapidly. You can't grab one individually, but lots of them, if they get in line and hit something, they make the forces of nature. And that's the particle view. So in that view, the vacuum is an incredibly intense flux of virtual particles, bombarding everything in the world, but each little particle hits so lightly you don't know it. But if they line up, you can get any amount of force or power you wish to from the vacuum flux. If we take the wave view, we find that from everything that moves in the universe, it puts out electromagnetic waves from all over the universe, and at each and every little region of space, there is an incredible number of waves passing through from all particles in the universe. And the total interference of all of these waves is extremely dynamic, incredible numbers of them, and so you have all this interferometry going all the time, and that's called the 0-point energy of the vacuum. You can never get anything less than that energetic from a wave viewpoint.
Oh, I'm glad to hear you mention the 0 point, because I think a lot of people are confused about what that means.
It means that if I have some process that I've built on top of that, when I stop everything that I'm doing on top of all of these boiling cauldron that is the actual empty space, the 0-point energy, when I get through with what I do and reach the zero there, we still have all this other energy boiling around. There is a bit of energy in the actual fabric of space that you cannot get below that.
Now you talk a lot about phase conjugation, and does that relates to the organization of these in the
Well, phase conjugation is a process which was known theoretically for some time, but we really only got going in it very well in about 1972, and really not very much then until the latter 70s, specifically after the Russians showed the work to Lawrence Livermore Laboratory in 1972. Phase conjugation is a very strange wave that we can make in response to another wave. But it has a memory, so to speak. The phase conjugate wave will back up exactly like a crawfish along the trail, the path through space the other wave took, no matter how tortuous.
So it's going this way, and then it has the memory and it comes back?
We have an object we call a mirror that's going to do the reflection. Don't think about shiny. It's not shiny. It's just nonlinear material. And in comes a wave, and what is going to happen is another wave is going to be produced that everywhere in space this other wave occupied, this wave will precisely superpose back along there, all along the path. It will go backwards, and that is a time reverse wave. We can't see time, so we see it as if it were going backwards in space. But it is a time reverse wave. It's moving backwards in its time.
Now, does that have something to do with what we were earlier talking about with the vacuum?
Yes, it does, because in the vacuum you're getting everything. You're getting everything you could possibly get and then some. The interesting thing, if you look at what's called ghost forms, momentarily, like watching your TV when it's bubbling away, momentarily you can see a little image or a little outline as if the bubbles got together just right.
Yes.
Well, the vacuum does the same thing. So momentarily there is the formation, for example, of a gold atom, or the formation of something that looks very like Tom Bearden. You know, they don't need much of that. But anything you wish to name, there's a momentary shadowy formation of the particles and everything to make that. It's not very much probability, but it is not zero. And when you have so many actions going on, I like to use the term the density of reality. In that sense, almost anything you can think of is real, but we're talking about how dense is it. Normally it's so thin that it is of no consequence. But we know from Paul Dirac that if you add energy to one of those forms, anything that's sitting there hidden in the vacuum, if you add energy into that form, you can in fact materialize it. You can lift electrons, for example, right out of the Dirac Sea, and you have a real electron born out of so-called nothingness.
Really?
But you had to add energy to do that.
So what kind of energy would we use?
Well, if we wanted to form things like that, we're doing it the other way around in the energy processes we're talking about. What we wish to do is we wish the vacuum to furnish the energy.
Exactly.
And we want to trick it into furnishing it in some form or direction that we can use. So our problem is to make it directional and make it have form and substance so that we can use it. And here we're very fortunate. We come to one of the great contradictions of electromagnetics. In electromagnetics, as taught from the universities, they really teach that all the charges of the universe are perpetual motion machines. They don't use the term, but they teach it that way. Because each charge pours out energy, and according to them, it makes the energy right out of nothing, which violates the master conservation of energy law. You can't do that. Nature doesn't do that. But what happens, they say, in classical electrodynamics is that it pours out all the energy that makes the fields and potentials from it that reach to infinity in each direction all across the universe. And it keeps on doing that day after day, year after year, month after month, century after century.
Which makes it perpetually motion.
So if you want a source of energy, classical electrodynamics already says that every charge in the universe makes energy out of nothing and pours it out for you freely forever. Quantum mechanics and particle physics, of course, have corrected that. We've known the correction for 40 years, both experimentally and theoretically. What really happens is the particle is absorbing all of these little tiny particle bombardments from empty space, the flux of space, re-radiating back some of that, but some of it, it acts like, more or less like, don't press the analogy too far, like an old spinning wheel. It forms a big enough form that when that form comes off the particle and is radiated away, it will grab any other particle and generate a force and translate it. So it turns some of the energy from this virtual state and knits it together and makes it in whole-size clumps that are now real energy and will move real systems.
Really?
Every charge does that.
Every charge does that. Now, is there a way to rephrase what you've just said so that, say, a teenager could really understand? Could you go through that?
If I have a gate in a river and the gate remains closed, all the particles of water that strike the gate reflect back into the river. But if I open the gate, some of the particles strike the bank, and then some of them strike where the gate was, and they go on through and they get gated out into the ditch that's going to run the water wheel. So the charge itself, because of its spin and a couple other factors, actually does some gating. It gates the energy from one form into another, changes the form of it into something we can use. And so every charge in the universe is already a little free energy system. All we have to do is learn how to use them correctly.
You've said that a lot of the information in physics and so forth that they are teaching is obsolete.
Yes.
and not accurate.
Electrodynamics has many inaccuracies. I have one slide with 32 major errors in classical electrodynamics, and that's nothing new. It's quite well known in foundations physics. I've added possibly a few myself, but most of them I collected from other scientists who worked in the area for many years and listed the errors. One of the things I just mentioned, it assumes the creation of energy out of nothing, which is false. We know that it takes it from the vacuum. So what this tells us is we do not have to go discover how to tap the vacuum for energy and extract the energy. The low charges already do it. Mm-hmm. We have the magic thing tapping the energy and giving it to us, the magic gate in the river. We have to learn how to apply it correctly, which we do not do. Mm-hmm. Another thing they did is Maxwell's equations have always, at the very beginning, included systems which put out more energy than you have to put in because they allow for this extraction and putting out of energy, mm-hmm. excess energy. Mm-hmm. That was an embarrassment because that's called asymmetric, and scientists love symmetry. Mm-hmm. It makes equations very hard to solve. Mm-hmm. So they did what they call re-gauge the equations. What they did, they changed the equations to where they didn't show that. They excluded that type of system that does that. They only kept those systems which don't do that, which is a small subset of Maxwell's systems. And the type of systems that they kept have been forced into local equilibrium. In other words, they assume the energy has changed freely twice in the system. Two free forces have occurred that would do work for you, except they only chose the ones that are equal and opposite, so they fight one another to a draw. So they chose to introduce totally ad hoc and totally arbitrarily additional stress in the system right out of nowhere, and to change the energy system twice right out of nowhere, and convert it to a system which cannot put out more energy than you put into it. Mm-hmm. And thereby they discarded far more systems than they kept and teach in school, but it made the equations easy to solve, and so that's what we're using.
Yeah, so we're still recycling the ignorance, aren't we?
Well, that was done by Lorentz well over 100 years ago, and what's happened is it's not diabolical. It got locked in when there were probably only 3 dozen electrodynamicists in the whole world, and everybody just kept putting it in the textbooks and teaching it, and most professors these days don't really realize what they're doing when they re-gauge the equations. Although you can go to Jackson, classical electrodynamics, he shows you exactly how they do it. But nobody ever tells you what's happening to the system when you do that. Mm-hmm. They say it's the same system. It is not.
Now, there was a thing about James Clerk Maxwell and Heaviside. Do you want to explain?
Well, what we're calling Maxwell's equations aren't Maxwell's equations anyway. Mm-hmm. Maxwell's equations are 20 quaternion and quaternion-like equations in 20 unknowns. So you can do all sorts of things in that kind of electrodynamics, his original electrodynamics, you can't do in what we teach today as Maxwell's equations. Mm-hmm. Oliver Heaviside took a look at that. Maxwell's book was published in 1873. Mm-hmm. The definitive paper was during the American Civil War in 1864. And quite old. We're talking something 100 and something years old.
Right, exactly.
Heaviside took a look at that, and he said, my goodness, you know, the electricians we have today, that's what they called an electrical engineer, and they really were about like a house electrician to wire your house up. They were not at all the collegiate electrodynamicists you expect to find today. And Heaviside, my goodness, these fellows will never learn that kind of mathematics. It's far too complex. So we've got to have a simplification. So he is the major leading figure who cut the equations down to basically 4 equations and 4 unknowns. Now, at one time, I resented that. I don't resent it anymore. I think he did the right thing. And the reason was, if he had not done that, to give them something they could get a hold of, get in their minds, understand, start to build telegraph lines was their big problem, for example, understand how signals went down a wire and so forth. If he had not done that, he was quite correct. They would have been another 70 years getting off of square one.
Really?
So I admire him for doing it. I think he did the right thing, but what I don't admire is the fact that they continue to teach those equations, and without telling all the young students that those are highly modified adapted equations and they are a tiny subset of the real theory. Now, That having been said, there are today, after sleeping for 100 years, electrodynamics is finally beginning to wake up again. There are now some younger fellows, real mathematical techniques and ability and great scientific ability who are chewing into electrodynamics and turning it back towards the higher algebras like Maxwell used, even going to Clifford algebra. They're giving us waves that travel faster than the speed of light, that travel slower than the speed of light, that have all kinds of energy in the wave, up to infinite energy. So electrodynamics is beginning to explode. You can go on the internet and go to the Los Alamos National Laboratory site, download papers by Rodrigo Sanlu, and you will find this exploding electrodynamics.
Now, you said something about, oh gosh, I should have written it down, but you said something about the speed of light. Now, people, I think the general populace sort of thinks that the speed of light is the maximum degree of speed that there is, but that's not true.
It's not true. De Broglie waves, for example, since their very inception, have always traveled faster than the speed of light. Slowest they can travel is the speed of light. Many other things, like in what's called the Coulomb gauge, the standard old garden variety potential common voltage would travel faster than the speed of light. So the question is how to get it in a Coulomb gauge. But these are quite well known. They're just not used. For example, there's a thing called quantum tunneling, and NIMPS, for example, and his colleagues have transmitted down a waveguide through a barrier at 4.7 times the speed of light Mozart's 40th Symphony. And thank you very kindly, you can identify the music. The music is nice. It is Mozart's 40th Symphony. So this answers the question for all time. You can't transmit intelligent information. Of course you can.
Of course you can.
Other scientists have done it not quite so fast, but faster than the speed of light. So now there's replicated experiments in the hard literature showing that, yes, you can transmit signals faster than the speed of light. By the way, speed of light is a very simple thing. It really represents in relativity a rotation at 90 degrees. That's all it represents. And if you say we can't go faster than the speed of light, really all you're saying is we can't rotate past 90 degrees. Well, if you use only 4 dimensions, so you only got one 90-degree angle, that's as far as you go. There aren't any other to turn to. But if you add a few more dimensions, you can turn and turn and turn forever, and there's no limit to the speed.
Interesting. And when you're talking about other dimensions, that means...
A dimension is mathematically it's just a degree of freedom where something can change.
Okay.
And it's not really that fundamental. It happens that in the world we normally observe, because of the processes we use to observe and detect in, the physical processes, we really only detect in 3 dimensions. We don't even detect time. Look at a clock. You don't see time. You see the spatial positioning of the hands.
That's right.
And after that changes, you infer by the change, the spatial change, you infer the time that lapsed. You never measured the time directly at all. There is no such thing as a true clock in the entire universe.
So how do they measure time?
They measure it by inferring it very precisely from the spatial measurements.
It's like an intuitive
yes,
thing, isn't it?
It doesn't mean that you can't measure it very precisely. You can, but you measure it from spatial processes and you infer it. You do not detect it directly.
That really, you know, when we're talking about the electromagnetic fields, that spectrum, the visible light spectrum is a very narrow band.
Yes, it's just one little... Actually, visible light is very interesting because if you take a harmonic interval, that means twice the frequency. The infrared at one frequency, if you freeze there and you go back up to the ultraviolet, far ultraviolet, you have the exact double frequency, twice that frequency. That's called a harmonic or a harmonic interval. So the so-called visible spectrum really feels is what's in between that interval. And it's just one little interval in a vast number of these harmonic intervals, both below that and above it. So it's just one little speck of reality, but a very useful speck because our eyes use that and we have all kinds of reactions with matter in that and everything. But light also goes down to where you can't see it. We can build special instruments and pick up the low infrared or the high ultraviolet and so forth. It goes on higher than that and gives us gamma radiation and things like that. Goes lower, and we can even go down to sound-type light radiation at any frequency you wish. In theory, it doesn't have much of a limit in frequency either on the low end or the high end. For practical purposes, with what you can do with your equipment you can build, of course, you don't get too far beyond the upper part of the light spectrum. You can get on off into gamma radiation and some other radiation. That's about as far as you go with equipment that you build.
Now, how does hyperdimensional physics work with free energy?
Well, the hyperdimensions, a set of dimensions, is a way to model something. It's a model or a description of processes, basically, is what you're talking about. And you make a lot of assumptions. Well, first you take an algebra and you take a set of coordinates and all of this stuff, and you frame a set of operations, like setting up a chessboard and setting up the operations that are going to be allowed. And then what you do, you find a set of physical phenomena, and you try to put correspondences between these phenomena and this chessboard. And you come up with a very special chess game, which is a mathematical model of the processes you're studying. It's never perfect. But if you get a good enough description, then this math model allows you to make predictions. You can design equipment from that, and with just a little bit of tailoring, the equipment will work in the area that you're studying. So the whole progress of science is based on producing accurate models, accurate enough to use and engineer and predict phenomena which is going to happen. We like to be able to predict when a comet's going to come around again and this kind of things. And because lots and lots of scientists have built these models on a special kind of chessboard that they set up, the model does make a legitimate prediction, and we can turn our telescopes and lo and behold, here comes the comet.
Now, when you're talking about free energy, you have made the statement that we're killing our source.
Yes.
Can you explain that?
As we just explained, the charges themselves, normally the charges occur in equal and opposite. You got about as many positive charges as you have negative charges all mixed together, and so the net result you're going to get out of that is nothing. It's not going to give you any free energy. But if you separate the charges, you move the positive charges over to one end, you move the negative charges over to the other end, you have what's called a dipole, two poles. Two different charges at each end is what we're talking about. Well, now the charges at this end are producing energy, and the charges at this end are producing energy, so now I've got a very useful energy producing critter. And it sits there from now till the end of time, as long as it stays apart in that fashion, and according to even standard electrodynamics, it pours out energy. They say it creates out of nothing. We know from particle physics it takes it from the vacuum. That having been said, suppose I have a battery and I'm powering a system that's connected to it. A couple of wires leads out to some resistors and a motor or two and a light or two and a fan or two and this kind of thing. It turns out the battery doesn't furnish any energy to the circuit. Certainly doesn't furnish any power. You can't furnish power to a circuit. What the power is created in the particular component that scatters the energy. So the whole business that electrical engineers use about furnishing power is an oxymoron. It contradicts itself. So what we have is the dipole, as long as it stays separated, will pour the energy down the circuit. Now, strangely enough, we know that the energy fields all the circuit, all space around that wire, out to an infinite radius in all directions. So actually the dipoles extract enormous energy from the vacuum and pour out enormous energy, but the circuit doesn't catch all that. The little surface charges in the wires going down to the circuit from the poles of the battery get struck by the little bitty sheath of flow that strikes right there on the surface and gets intercepted and diverged into the wire to power the electrons. All the rest of it misses, just roars off into space and is never collected, never used. A nominal circuit, a little simple thing, a little simple battery powering a little simple flashlight light or something, produces about 10 to the 13th times as much energy as the circuit actually intercepts and collects and uses. So in the first place, we are terribly, terribly, terribly inefficient at collecting and using energy, which is where we should be putting our effort, because there are ways to increase that. It doesn't have to be that way. And some of them are even known in the literature, but everybody's using this single pass stuff where you only collect a little of it and says, therefore you can't power very much and you got to keep doing a lot of work. Now what does the battery do? It doesn't furnish anything to the circuit. Because the way we build it, the top part of this circuit has greater flux on it to push the electrons, and so the electrons get forced down with extra potential on them, and they scatter this energy in the resistor. That would be heat. The resistor is producing heat to work for us. Maybe we've got a heater in the corner. But when it gets down to the bottom line, it doesn't have any excess energy left on the electrons. They're just, so to speak, for our purposes, dead rocks, waiting to be pushed. just so much inert things that have got to be forced against resistance back up through the dipole. So what do? We build a closed circuit. We pump all the spin electrons back up through the dipole and knock those charges every which way. So we destroy the separation of charges that was furnishing all the free energy from the vacuum. We just knock them apart. Then the battery has to use chemical energy. It has, through its chemistry, it has to again furnish separated charges, do some work to force the charges back apart, so we restore the pump, that we open the gate in the river again, so the water will flow freely. And then we knock it apart again. It furnishes some more energy. When it runs out of chemical energy, we got to stop and recharge the battery. But the system was always a free energy system.
Okay, so say I've got a battery and I've got connections hooked up to what you would call the dipoles. Is that correct?
That's right.
And I have a positive and a negative
That's right.
charge. And I've got this hooked up, say, to the fan. All right, now where in this circuitry am I collecting the energy?
You're collecting it right there in that separation of charges, where you've got a whole bunch of positive charges on one end of that pole.
Okay, where my connection is on the positive.
Right at that connection.
Right at that connection.
And right at the other connection on the bottom, though the terminal right there, which has all these positive charges collected in it, is going to be pouring out energy that it takes right out of the vacuum.
So how would we contain the energy at those collector points in order to have that constantly recycling so the battery doesn't need
Well, what we
die?
have to do, the basic requirement is we must not have to take half the energy. Half of it went to the resistor if there were no other losses.
I need you to put this in real simple terms.
Okay.
Because those of us who don't have a technical understanding of, of all of this, we need to really
Okay,
use
simply put, here it is.
simple foot.
The first requirement is I must not kick apart the dipole. Okay, that means I must do one of two things. Either I must not ram the spin electrons back up through the dipole the wrong way, it's trying to push them the other way, and knock the dipole apart, or I must trick this dipole and trick those electrons so that they wish to move of their own volition from the bottom line up to the top.
A voluntary movement.
Now, both ways can be done. One way to do it is don't even have a circle, just surge the current back and forth. That was Tesla's favorite way. In his magnifying transmitter, he went from the top to the bottom. He didn't actually have a closed loop, so he didn't knock his dipoles apart. It was a matter of timing from then on. The thing that we're working on in CTEC, we have discovered a process that we call bridging. And the idea is if we can cause a little time reversal zone right where that dipole is.
Which means time reversal, we're going this way, we're coming
means
back.
the videotape runs backwards.
Videotape runs
Now,
okay.
let's talk about a time reversal zone.
Okay.
When we took physics and we took electricity in school, they taught us that two like charges repel and that two unlike charges attract. That's true as long as time is running forward.
But
It's
when
not
it's
true
reversed,
when time reverses. It's exactly the opposite.
like attracts like.
All right, so if I can get a little time reversal zone in here, which I can do with phase conjugation, if I get it just right,
That's this
when the
phase
electron gets
conjugation
to
when
the
they're all in
bottom,
order.
he says, I'm supposed to fall down back to this position.
I can't play the
thinks
game anymore.
He's
I've got to
not playing the ram it up through the dipole
Right.
forcibly. He's
Right.
playing fall down the stairs. He thinks he's falling down the stairs
Right.
freely.
Right.
And so the electrons will appear against, the way we see from outside, we see it moving against the voltage. That's called a negative resistor, by
That's
the way,
like
when it
swimming
does that.
uphill.
That's right. It's like the water flows uphill of its
Yeah.
own volition, which it will do if time runs backwards.
Right.
Take a videotape of water running downhill. Run the tape backwards, the water's running uphill.
That's right.
And when we do time reversal, that's exactly what happens. So our problem now is to trick this thing so that the water runs uphill in that little point only. And from there on, it runs normally. If we can do that, we can furnish just a tiny bit of energy from the left to a component where the trickery occurs on the right. We can circulate the current through the load on the right, and we can do it with very little cost to us on the left. And that's called a bridge. We have one component that will make that bridge. It's not in production yet. It is the Fogel semiconductor, and when that semiconductor hopefully gets in production, hopefully about mid-1999, then we'll be able to do exactly what we just said. In the interim, I might add that it appears that a very fine scientist, Dr. Chung, at the University of Buffalo has in fact come up with a true negative resistor, which would be doing this thing I just talked about. Because Dr. Chung has reported at a conference that she has some carbon filament, crossed filament material. She is one of the world experts in smart materials, where the materials is used as electronics.
Oh, yeah, it's very good to explain what smart materials are.
The material itself, the little pieces of the material act as little pieces of electronic circuits. Very intelligent actions. And so she is one of the world experts in that, probably the leading expert in the United States. And so she has reported, and a paper I understand has been written and is now in the referee process for publication.
Excellent.
Describing this resistor, which in my interpretation does exactly that. And so if so, Professor Chung has in fact come up with a very practical component which will eventually be capable of being mass produced very cheaply, and it will in fact give us that magic bridge, which means that we can produce over unity systems practically.
There's a lot of opposition to this, isn't there?
Yes. The conventional folks who have never thought of time reversing the right side of a transformer, for example, the secondary, are very much in objection to that, because if you apply normal electrodynamics to it where you don't have the time reversal, it doesn't work. It couldn't work. Even in theory it couldn't work. Well, you see, this is the problem. We have people discussing something from a different model. In the model that they are saying this cannot work in, it cannot work in that model.
Right.
But all that says is you've got to be using a different model where it can work. Now, Dr. Chung is obviously not using that conventional model. She's using a model where the time reversal does occur. And if that occurs, then she jolly well can get the electrons to flow against the EMF or against the voltage as far as we would see it from outside. As far as they see it, they're flowing downhill all the time. And you can build a bridge, and you can build a true over unity system, a negative resistor. And I think we'll see them coming out of the University of Buffalo. I think they hold the patent on this. They have filed the patent. And I think you will see devices coming out of the University of Buffalo under the work of Professor Chung.
Interesting. But that's not the only place that this is happening either, though, is it?
No, there are several. We've known processes for many years. It's just nobody has accented it that do produce more energy out than you put in. To say that this is impossible is ridiculous, because it's already in the literature and has been for 50 years. Anti-Stokes emission, for example, is defined as a case where into the material you put some energy, and the material puts out more than you put in. Does it every time, any hour of the day, a week, any month, a year, whatever you wish to. It will always do that. It's called anti-Stokes emission. The only problem they have is you say, well, where did you get the extra energy? And they say, well, we think it came from the internal energy of the molecule, blah, blah, blah. And you say, well, I'll apply the conservation energy over to the molecule. It didn't collapse. Where did it get the excess energy to furnish? And they say, I don't know. And they left it right there. They didn't chase the thing down to its conclusion. But does it produce more energy? Yes, indeed. Ledekoff, starting in 1967, and a lot of other scientists were showing papers in the literature in physics, in the leading physics journals, that showed a thing which they had to call negative absorption to even get it through the sensors.
Really?
Or negative resonance absorption. What that really means is excess emission. It means, again, you put in some energy, it gives you back a lot more energy. Now, recently, I say recently, the last few years, Dr. Lawande has had, and his colleagues have had a very formidable paper in Nature. And Lawande has a beautiful example of that, and I'd like to describe that experiment.
Okay, great.
Because it can be done at any university for $20.
Great.
It's so simple. You take a little glass or flask of water, and you put a little bit of dye in there that fluoresces to some radar, some laser frequency.
Right.
And you use a little weak laser, very, very weak laser. And let's say you fire one little laser pulse into this beaker full of water with a little dye in it. You get a little warm red glow around where the beaker strikes. Just a little red dot of light. That's all you get. Nothing. Not interesting at all. I shined in, I hit it with a laser pulse, got a little red glow pulse, and that's it. Then I do one change. I reach in my pocket, like the Cajuns say, where I carry it there all the time, and I pull out some titanium dioxide particles. Now, titanium dioxide is a main ingredient in white paint, so it's dirt cheap. But these particles are sized through a filter screen carefully so that their resonant frequency is at the same frequency or very near to this little laser I'm using. In other words, if the laser light hits a little particle, it don't just push it, the little particle vibrates. That's all that we're talking about. Now I pour these little particles in the solution, right out of my little test tube here, my little vial. And now I have the same thing I just had. I have my little laser, I have a little fluorescent dye in here, I have the little particles, and I now fire another pulse. I don't get just a little warm glow. I get a tremendous blast of light that comes out of this thing, fills the whole room.
Wow.
And obviously has much more energy in it by far, and it's all coherent light. It's like a laser, filling the entire room, and that's called lacing without population inversion. Lawande has several nice patents on it and several nice descriptions of it. So here's another process that you can test in any university, sophomore level, certainly junior level, optical lab, anywhere for $20. All you got to do is size the particles. It's that simple.
Interesting.
And over-unity processes do exist, are known. There are probably 8 or 10 more in the conventional literature that always put out more energy than you put in. Now, my question is, why aren't we using these or adaptations of them as power systems?
Exactly.
Because if I'm putting out 20 times what I put in, for example, the resonance there can give you 18 times. 20 is not a bad figure. So we know we can get 18 or 20 times out what we stimulated it with. Well, I could take, even with a 50% process, I could take 2 parts of that 20 and feed back in to run this gadget, and the other 18 would be for free. It'd be just like a heat pump. The average heat pump on a home, under ideal conditions, has a COP, put out over what you put in, of about 4.0. It puts out 4 times as much energy as you're going to take from the electric line. Now, the reason you can't do a free energy device where your home heat pump, because you can't keep the conditions ideal. As it gets colder, its efficiency goes down, and you've got to switch over onto the resistors, and now you don't have COP4, you got at best COP1, actually it would be about 0.9. And so you got to pour more energy into the thing to run the motor and blower and all that than you possibly can get out of it. So that keeps you on the power line, keeps the power meter on your house. Otherwise, you could cut loose with your home heat pump.
I think people would like that.
Well, they would, and if you build a real efficient heat pump, well, you get in a lot of trouble. There are indications from various people in England, for example, who have built in the past some fairly efficient heat pumps at low temperature and very slight differences. And those people ran into enormous legal difficulties and scientific difficulties and personal difficulties, and they just never got out anything that was able to get out anything that worked. But they did build processes which were much more efficient as the temperature dropped. So one of the things I would like to see is, you know, some high publicity from the newspapers and everything forced into that area and force these fellows to work on high efficiency cold processes for heat pumps. Because there is one that, you know, everybody can understand. It's simple, it's cheap, you got it in your home, it's already 4.0, so you could hold it at 2.0. That's fine, that'll do the job. But that would also get the power meter off your home, and so that's not likely in the near future. But it is something that is known. You can look at the textbook and see it's 4.0. It's not Tom Bearden talking. You already got it working in your home. They call that lowering your power bill by having these more modern heat pumps. You got one that's 4.0 now instead of 1.3. But they do exist. They're in all the homes, and there's no reason why we couldn't pursue that line of endeavor to come up with something that would be very useful in the power industry.
Do you think that if they came out with some applications of this over unity in less restricted areas, that, you know, smaller forays into smaller appliances and smaller things, that maybe using their same modality of gradualism, that we could really use, you know, progress in that, on that vein?
I think we're likely to. I think you're exactly right. And where I think what's going to drive it probably will be something like laptop computers, where you really want a powerful little computer. You want to be able to carry it with you everywhere you go. We need to do everything. Well, the computers are getting powerful enough, but it's the problem with the battery. How to keep it powered, you see. You want to be able to use it when you're out in the wilderness and not even near the power line.
Exactly.
So the point is, you're going to carry a big battery with you if you're going to use it all the time for 6 months. Or wouldn't you like to have a little device that would just power the thing? So I think right now they're just under a tremendous drive to get more efficient batteries, and they're getting more efficient batteries. It's steadily growing. But I think in the future you will probably see one of the really free energy machines, free energy little power systems, to power really laptop computers and other similar machines. It's also, if you went camping, it'd be nice to have the thing to make coffee in the morning, you see, when you got up from the campfire.
Exactly, exactly. I just see that it's starting off in a smaller format and gradually moving up. Now tell us about Patterson cells.
The Patterson cell is a variation of, before I speak of that, I need to lay the foundation for one thing.
Okay.
I went through a process of one pass collection. The energy went down the wire at almost the speed of light, or essentially at the speed of light. The little surface electrons only got one grab at it to divert, like a board in the wind, or like you holding your hand out the window in the car and diverting a little air from it. It only got one strike at the flowing energy to divert it in there. The rest of the energy then flowed on off. It wasn't collected, and you never got another pass at it.
Right, wasted.
And we said there was an enormous amount of energy that's wasted. There's 10 to the 13th times in an average little circuit that is missed.
Yes.
Enormous amounts for this tiny little bit we catch. So a dumb country boy like me would say, well, suppose we could retro-reflect that energy flow. Suppose we could bring it back again and let him have another pass at catching some more, a little catcher's mitt, and then retro-reflect it back again and catch a little more. Well, obviously, every time you hit him again, he'll catch a little more. That's the law for that's already in physics. So he would catch more energy, and to us, where we calculate only from the single pass, he would look like an over-unity process.
Exactly.
The energy is there. We're describing, really, if we want to be very technical, we're describing an open system where the energy is coming from a free external source, and we're just getting more of it into the system, catching more. So there's nothing in the laws of physics or thermodynamics that's being opposed. You're not violating conservation of energy. It's catching more and using more. So this would be the way to go, would be to have this multi-pass, multi-collection. Well, it turns out when you do that, you have to revise a thing in physics called the work energy theorem. I've already done that, so it's already there and it's in the literature. Basically, it says you got more than one pass, so you catch more energy than what you normally calculate for single pass. That's all it says. Now, in materials, there are some materials that will do this for you. That anti-Stokes emission is a type of materials that will do it. And the thing I talked about with the little particles, the little titanium dioxide particles, to do the Lawandi experiment, the little particles are doing it. When the laser pulse goes in, the light gets broken up and reflected back and forth, and it stays in, and it's being collected every time it hits anything. And it makes lots of hits and lots of collections before it gets out, before it finally escapes. So the more hits, you know, instead of one hit, we've got hit after hit after hit where it's collecting energy. The little particles
just accumulating.
So the little particles showed you they had the energy by giving you this huge blast of energy to show you how much they collected. And they sit there and take a bow for you after their performance.
Yeah, they're saying, say, hey, look at me.
Look at me. So this is another way to do it. Do it with intensely retro-reflecting or intensely scattering media is what they call it in physics. And Lawandi, of course, has filed patents on one that will do this lacing without population inversion. You don't have to do all this crazy stuff you do in normal lacing. Well, if we have one here that will do this and do it down at, say, infrared, now we're talking heat.
That's right.
You see, we've gotten away from the middle of the band and from the top end of the optical band down to the bottom. We're not really that far from where the cell was working with Lawandi's cell. We just came down a little bit. So we didn't even have to go a full harmonic down to get down to the heat zone. So if we can get it to work down in the infrared, then we can have something that will produce heat. And it'll do exactly the same thing. If it retro-reflects it back and forth before it gets out, it'll collect and collect and collect and collect and give us lots of heat. Well, Patterson's power cell will do that. What he does is he coats, he has these little micro spheres of plastic, and he coats them with palladium. A cladding, a palladium metal. Now, palladium has a beautiful characteristic. It loves hydrogen. And so the palladium will scarf up all these hydrogen ions that are running around in the water, and that's, by the way, just free protons. And it'll scarf them up and fold it into its lattice. It just loves to do that. And we call that loading. So the palladium will start to load itself. And you say, oh boy, you give me a lot here to load up my plate with. Because you put this solution in here and it's got all these nice protons, and boy, am I going to gather them. So he gathers in all the protons and and when he does, he starts to create some of these little time reversal zones. But also, the energy that Patterson is putting in electrically starts to ricochet back and forth between the loaded palladium. Mm-hmm. The loaded palladium starts to retroreflect. And what happens
creating
is
energy there.
You get more and more collections now
Right.
instead of just one pass.
Right.
And so more and more heat starts to come out of this thing. And it gradually grows as the process rises. You run it for, I think it's some 12 or 13 hours in the good one that he had. And it will gradually come up till it's putting out somewhere between 1,000 to 1,200 to 1.
Wow.
Now, when you cut the power off,
Right.
continues to operate for another 8 or 10 hours as it gradually dies down.
It dissipates.
He had a problem.
Mm-hmm.
He proved it conclusively. He's got a patent. It's been independently tested and verified by at least 3 universities and a couple of spooky government groups, which I don't even know who they are, but they snuck in and did some tests.
Some black budget
Whatever,
stuff.
but it's real. It's absolutely real. If you don't believe it's real, you can go there and probably get with Patterson and test one.
Sure.
But the thing is, it didn't turn out too practical with the palladium because the ions, the heavier ions in the solutions, beat the palladium, and so it beat the cladding gradually off there. But it proves the principle.
So it's unstable. Mm-hmm.
So but as the cladding folded up and came unglued,
Sure.
it broke up the geometry and it
broke
stopped
it.
it. Now he has one now with just copper, which won't do that kind of loading, and the efficiency goes way down, but it's still over unity. I understand it's anywhere like 1.2 to 2. Which is certainly dramatically different from 1,000 to 1, but it's
Right.
still more than 1 to 1.
Right.
And you can independently measure it. So the point we're talking about here now is merely a matter of development. We are talking about something already proven, already established, already recognized by the U.S. Patent Office, and a patent granted. In fact, several patents granted. So what we should be doing is we should be having enormous resources focused on a Patterson power cell for development.
Exactly.
How can we keep the palladium on, for example, and get that 1,000 to 1 without it beaten up? Things like this is what we should be doing. And if we had a real good Department of Energy, that's what they'd be doing instead of off playing great big cyclotrons and accelerators and
Yes.
big nuclear processes. This is where the action is. 10 to the 13th is a very large number. If we can collect a little bit more out of that by multi-reflection and multi-collection, then we don't need all that other big mess and all the nuclear waste and all that. We need a working model process like this. And, of course, Patterson has shown you the way to go. Lewandowski has shown you the way to go. Letakov in Russia has shown you the way to go since 1967. Letakov has a paper in one of our nice journals, Contemporary Physics, which summarizes things. A nice summary article showing you this really is a true Maxwell's demon. It's like we had a little demon in there selecting all this stuff and giving you free energy.
Wow. Now, I understand that Patterson cell is really valuable for, say, these nuclear power stations, that it can
Yes.
take care of the waste that's such a problem.
You've just mentioned the thing, and I'm awfully glad you mentioned it because it's something I very much want to talk about. I've spent, in the last 2.5 years particularly, enormous amount of work on it. If the work stands up, then I believe that we have solved the cold fusion problem. I had an if on that, and it remains to be seen whether the work stands up. But I want to explain to you what happens in cold fusion and why I think and why you can get over unity out of it. In cold fusion, it's not really a fusion process at all, but what we do, it's an electrolysis process. It's in water. It's very similar to the Patterson cell, which is really an outgrowth of that. But we're putting the electricity in and we're getting heating and we have calorimeters and instruments measuring it. Now, by the configuration of the experiment, the scientists have not known about these time reversal regions.
They haven't known about that?
They haven't known about that at all. That's my contribution.
Oh, wow.
That a
Well,
time
thank you.
reversal region can form in a solution. And you ought to take that into account, and you ought to deliberately design to optimize the process. Because let's speak about now, suppose I get a little time reversal process to occur. And it occurs as the palladium starts loading. And it's directly coordinated or correlated to the loading of the palladium. When it gets sufficiently loaded to where you would expect time reversal zones to start occurring,
Yes.
and they'll last, and then the fluid moves, and so then they collapse.
Right.
But they're forming and gradually decaying all the time in the fluid. Now, once you have the palladium loaded. And that is the correlation. You don't get the excess energy till the palladium loads. If you load slow, it takes a long time to start getting energy, 3 or 4 days.
Well, sure, because they have to bond and get together
you have
and,
to get
and
this
have the
happen
energy
before
going.
you get all that multi-reflection.
Exactly.
And that is a phase conjugate reflection. That's what a time zone reversed
Right.
is. In this time reversal zone, a very marvelous thing happens. Marvelous, beyond belief. Remember I said they taught us only half the laws of electrodynamics about particles attracting and repelling. Now I have just invoked the missing half because my time now is reversed in this little zone I'm looking at. It means that two like charges will draw together, not repel each other.
Right.
And what is floating around in that solution? Hydrogen ions, which are just free protons. So the protons will cluster together in clusters, and they will form quasi-nuclei. Now, Pauli exclusion principle says you can't time reverse one proton or one neutron or one electron, but you can do 2 or 4 or 6, but you can't do 1 and you can't do 3.
Right.
But you can do 2, 4, 6, 8, like that. So let's look at the case where we have 2 of these hydrogen ions, that is, the protons, have now drawn together. That's the same form as a nucleus that has 1 neutron and 1 proton. We call that an isomer when you don't care whether it's a neutron or proton. They're always changing into one another anyway. They just flip a quark and you turn a proton into a neutron. Flip it the other way, you got a neutron again. And they're doing that all the time. It's a dance they go through. So they don't just stay a hard proton and a hard neutron at all. They're changing into one another all the time. So you got a dynamic process you can shift for 1 more neutron or 1 more proton.
Right.
So we have these 2 protons together and we're in a time reversal zone. That's a perfectly stable configuration at a certain strength of time reversal. As that starts to decay because the fluid is moving and moving back out of that configuration, suddenly this is an excited state. It's not a normal state. Well, excited states decay. They emit something or do something to change, to balance the energy, go to a lower energy state. So what happens is 1 quark and 1 proton flips, that makes a neutron, and that is deuterium. And that's where the deuterium comes from. Here's the part that has frightened all of the normal high energy physics.
Okay, we're going to have to really scurry on this because we're running
out
out
of
of time.
It doesn't need high energy physics. This is the electronuclear reaction, the use of time reversal zones and clustering and quark flipping. That's all it is. And that's what's happening. We're changing the nuclide. Now, suppose we get 4.
Then we double it.
Well, I now have 4 protons stuck together. If I flip 2 quarks, which they will do as the thing decays, it'll flip 1, and that's still an excited state as it decays further, flip the other, and that's 2 neutrons and 2 protons. That is a helium-4 nucleus, and it's what we call an alpha particle. And in the August conference where I first presented any of this, this year, Hal Fox made an impassioned plea for anyone who could explain where all his alpha particles are coming from in his experiments, because he doesn't go in there with all these helium nuclei, and he comes out with them. Well, I already had a chart with the interaction on it which generates those particles.
Really?
Now, at the same time, we have charged up, I'm just going to say this briefly and not go too far.
Yeah, because we're really at the end of the show.
Charged it with time. When time decays, it's energy compacted by the factor c squared, just like mass is. It's the equivalent of atomic energy.
Wow.
When you charge a particle with time rather than energy, and when it decays, it charges very slowly and it decays very slowly. Coordinated again to the palladium loading. When I start having some of this discharge, it comes out and winds up as normal transverse waves and gives me excess energy. And that is the excess heat that is occurring in the cold fusion experiments. We also explained all the anomalies in the instruments that are occurring at China Lake. So we got 100% fit to it. Doesn't prove it, but it's the first requirement. Got to be consistent.
That's wonderful.
But it will fuel the world. Now, what's the bottom line? Burn time.
Okay.
Burn time for
Burn
fuel.
time, and that's going to be our ending. That's the last moment.
Right.
Wonderful. Thank you so very much. I'm sorry we didn't start maybe a little earlier with that, but
thank you, Elaine. It's a real pleasure.
We did get a lot of that in. So thank you so very much for being with me. And to my viewers, thank you very much for tuning in. Join me next time when we explore another avenue of